Okay, let's move to practice problem number 3. As you can see, these are not short problems, but hopefully you'll develop kind of a rhythm to doing these hypothesis tests. Okay, in practice number 3, we got something brand new. It says a meteorologist claims that the average wind speed in their city is 8.0 miles per hour. A sample of 24 days has an average wind speed of 7.6 miles per hour. The population is normally distributed with a population standard deviation of 0.6 miles per hour. Okay, we got all this data. We got our sample, we got our sample size, standard deviation. Okay. One thing you might notice there, the sample size is only 24 days, right? That's less than 30. Does that mean we can use our ideas of the central limit theorem and the formula for the central limit theorem? And you notice the next sentence begins with the population is normally distributed. So even though our sample size is less than 30, that's okay because the population is normally distributed. So kind of that same theme of when we can use the central limit theorem formula for the z-score, right? That's all still in play. All right. Then at the end, it says at alpha equals 0.01, is there enough evidence that the average wind speed is not 8.0 miles per hour? So the meteorologist claims that the average wind speed is 8.0. Is that really true? And you notice how that question is phrased. Is there enough evidence that the average wind speed is not 8.0 miles per hour? So we're going to begin. We're going to do the hypothesis test. And we don't have it broken down in the parts, but we're going to go through each step, right? So step number 1 is to state the null and alternative hypotheses. So here we go. Step 1, and we'll begin with the null hypothesis. Again, we assume there's no difference, right? The nothing hypothesis. So h sub 0, we assume that the average really is 8.0. Even though our sample data says something else, we assume that everything is exactly what they claim, right? Mu equals 8.0. The alternative, and here we got to be really careful with that wording, is that it's not 8.0. So H1, mu does not equal 8.0. Okay. Now let's pause here, because whenever you get a hypothesis test with a not equals, there's an extra element to it that we want to be really careful about. Okay, so here's the idea. Think back to that graph we drew at the end of the previous problem. We're going to do it here at the beginning just to be really clear what's going on. So we're going to draw our bell curve. We're going to put our mean 8.0 there at the center, right? Now, they said we're testing not if it's bigger than 8.0, not if it's less than 8.0, but is it simply not equal to 8.0, right? Is the meteorologist telling us the reality, right? Or is it not actually true? Okay, so think about the significance level and how the shading is going to work. So we're saying alpha equals 0.01, right? That's what they tell us in the problem. If you ever get a not equals situation, then you have to divide this in half, put half of that number at the top and half of that number at the bottom. Okay, so we divide that in two. So 0.01 divided in half is 0.005. So 0.005 at the very top, and the other half 0.005 at the bottom. So in total, it's 0.01. We refer to this as a two-tailed test. And we use whatever the significance level is, alpha, divided by 2 in each of the tails. All right. In the previous problem, we had a one-tailed test. It was a one-tailed test. We knew it was because at the very beginning we had a greater than in the alternative hypothesis. So when we see that greater than, that means we put all of the alpha at the top. And we're just asking, based on our sample data, does our p-value land up into that shaded region? Here, when we're asking simply does not equal, we would have enough evidence if either one of these occurred. So if we land in this shaded region, that's enough evidence that we don't equal. Or if we land in this shaded region, that's enough evidence that we don't equal. Either one can happen. So the way that statisticians choose to do this, they take that alpha and they stick it in both, half of it in both the upper and the lower, as opposed to here when you take the full alpha and put it up at the top. So really, what does that mean? The thing is, the statistician chooses the alpha level at the beginning. So you always have to choose this before you go through your testing. So they know what they're doing. And they wanted there to be 0.005 in both tails. And then they said, okay, if we want 0.005, then together that would make 0.01. Right? If they wanted 0.01 in both tails, then they would start with 0.02 here. And then say, okay, 0.01 here, 0.01 there. Also, something more, while we're talking about significance levels, it's a good time to point this out. The smaller the significance level, the more difficult it is to have enough evidence to reject the null hypothesis, right? So in the previous problem, we had 0.05. So we just had to get in the top 5%, right? Not easy to do, but that's all there was. Get in the top 5%. With this one, 0.01, well, that's even smaller, let alone we then divide it in half. So here we either have to get into the top 0.5%, like in the top 0.5%, or in the bottom 0.5%. This is going to be very difficult to do. Well, it's not that it's hard for us. I mean, we just crunch the numbers, but there has to be a lot of evidence in order to, get this high up or this far down. Where before, it's still not easy, but, geez, 0.05, that seems like a lot more realistic than, okay, anyway, let's keep going. Once we have our null and alternative hypotheses, let me keep this close by actually. Once we have those figured out, we will then go to calculate the test statistic. And that's based on our sample data, right? So here we go. Let's set it up, step 2, and let me just cover this up for the moment, show you where these numbers are coming from. Okay, so we got our z-score. It's the central limit theorem formula. So we got our sample average, right? The average wind speed from the sample was 7.6. We subtract what we assume to be mu. So mu is 8.0, assumed to be 8.0, 7.6 minus 8.0. We had a standard deviation of 0.6, and it's divided by the square root of our sample size, 24. Okay, and you notice I've drawn some parentheses here and here. If you're going to enter that into your calculator in one shot, be sure to use parentheses there and there. And you should get this number, negative 3.27. And just to be clear, that's a z-score, but of course we now refer to it as a test statistic. Okay. In step number 3, we want to find the probability that is associated with that test statistic. Let me erase this, just talk it out. The p-value. What probability goes with this z-score? So I'd encourage you, start off this way. Probability that capital Z leave that space blank, and then fill in your z-score, negative 3.27. Now here's the thing. So I told you back in the first problem we did, you'll fill this in with either a less than or a greater than based on your alternative hypothesis. Trouble is, this time, our alternative hypothesis is a not equals. But we do need either a less than or a greater than here. So which one do we pick? Okay, so we have to look a little bit further. How do we know? Because that's just not equals. We look at our sample data results. What was the sample data? The average from the sample. Was it bigger than mu or was it less than mu? Our sample average was 7.6. That's less than our mu of 8.0. So if this number is smaller than this number, then we use a less than. You could probably argue the same thing. You know, we did the same thing back in our first example, right? So this was practice number 2, right? So we had a greater than, so we knew here we needed a greater than. But we could have said, made the same argument, right? So our x bar was bigger than our mu, right? That number is bigger, so we use a greater than. Kind of same idea. Now here, we can't tell from the alternative, but we can see this number is smaller, so we use a less than. There is one other way to tell. It's kind of based on that same logic. Is your test statistic positive or negative? That's another way to do it. If your test statistic is negative, then that means you're on the lower side, right? You're on the left side of the mean. If your test statistic is negative, you should use a less than. If your test statistic is positive, then you should use a greater than because you're on the upper side. Okay, it's all getting at the same thing. I kind of like that first way, right? If this number is smaller than that, use a less than. I think that's hopefully pretty clear. Okay, so at this point, we could use a table of z-scores. You can do that if you want, but I will encourage you to use the Statcrunch Calculator. So go on into Statcrunch, bring up that normal calculator. Just use the standard, right? Z less than negative 3.27, and you should get this right here, 0.00054. Okay, so we got our p-value. In step number 4, once you have the p-value, now you compare to the significance level. So here's how that's going to work. For this case, again, remember you're comparing to actually half of the significance level. So we got 0.0054 for the p-value. Let me erase that just for the moment. We actually want to compare here to alpha over 2 because that's how much is in the lower tail, right? We're really just looking at what's less than 8.0. So because our sample average came out to be 7.6, we're wondering, okay, I know 7.6 is down here somewhere, but will 7.6 be in the shaded region or will it be up here? So we're only comparing our p-value with 0.005. Okay, so our p-value is this, our 0.005 alpha over 2. Which one is bigger? Which one is smaller? Well, oh, that's got a lot of zeros. Alpha over 2 is the bigger one. So what does that mean? If that's our p-value, it's smaller than this. That means it went beyond, it went into the shaded region, actually pretty far into that shaded region. There's our p-value of 0.00054, way down here. So that's where that 7.6 average landed. Doesn't seem like much, but the significance there, that turns out to be a big jump probability wise. So what does that mean for step number 5? Do we reject or do we fail to reject? Well, if our p-value is less than our significance level, then we reject. There is enough evidence. We landed in a shaded region. There is enough evidence to reject the null hypothesis. In other words, there's enough evidence to say it's guilty, if you will. And so there you go. If you'd like an interpretation, well, I guess I have a drawing there. Yeah, there you go. Okay, we've kind of been drawing this as we've been going. So yeah, the 7.6 landed way down in here. That p-value, very small. It goes beyond the 0.5% even. Tiny little p-value all the way down on that end. And yep, okay, looks like I was explaining it here again. Does P fall inside the shaded region? Yes, it does. And now here's the interpretation. If we reject the null hypothesis, then that means there is enough evidence. There is enough evidence that the average wind speed is not 8.0 miles per hour. Okay, one thing we got to be really careful about here is the way we phrase this interpretation. Notice at no time does the 7.6 come into our statement, because that's not what we were asked, right? The question said, is there enough evidence that the wind speed is not 8.0, right? This just happens to be the value we got from one sample. We're not trying to make any claims that this is the true average. No. We're just saying the true average is not this. There is enough evidence that the average wind speed is not 8.0. Okay. Very nice, very nice. A lot of tricky logic with these. A lot of tricky logic. And so if you're still struggling with that, hey, come talk to me and maybe we can make sense of it, make better sense of it, explain it from a different point of view. The logic with hypothesis tests is no joke. Okay. But hopefully, you begin with just the process, right? So start with just, can I go through the steps? Can I remember that if the p-value is less than the significance level, then that means reject. And to reject means that there is enough evidence. Okay, so start with the procedure first, but then as you're practicing that procedure, be thinking, okay, why is this what it is? And if you're wrestling with that, like a lot of students do, hey, come talk to me, talk to a tutor, and bring it to that next level. Because that's really going to help these problems flow for you, just to understand really why we do what we do. Okay, I'm going to stop this video here.